So first of all, I'd like to thank tonight's sponsors, which are Hexagon and Northern Survey Supply. So we've got Matthew Brown and Bruno Lalonde on the call tonight, and they're going to, just after Brian's done talking, they're going to share a little bit about their company. So I'd ask everybody to make sure that you stay online and so that we can learn a little bit more about Hexagon and Northern Survey Supply. Next slide, please. All right. So tonight's speaker is, of course, Brian Buss, president of BWB Consulting Services Incorporated, and his talk will be on the use and misuse of explicit and empirical data in the mining sector. So I have known Brian, or known of Brian. He's most of my professional life, and in our personal life too. His daughter actually babysat my kids when they were young. He's an outstanding engineer and an outstanding man, and a great mentor to a lot of younger engineers and a lot of older engineers, myself included. So I'd really like to thank him tonight for sharing his time with us, and I'll ask him to move ahead with the speech. So we're looking forward to it, Brian. Oh, and for everyone else who's on the line, I'd ask you to make sure you mute your microphone so we don't get any feedback. Thank you.
Okay, well, first of all, thanks to everybody. I'll just submit for sharing my screen here. We'll manage through that. Let's see if this comes up okay. Can we verify that you've got my title slide?
I can see it, yes.
Okay, perfect. Well, thanks of all to Neil for reaching out and asking me to participate tonight, and especially the rest of the team, the organizing team at CIM in Sudbury, of course. And I'm a long-time Sudbury native, 30 years living in the city, 20 years working for one of the big mining houses there, Vale. And I can honestly say there's no better honor to be given to someone to ask to share their experiences and observations with their peer group and colleagues, which I think is what I view this audience as. So thank you very much. I will note that if I can't get to your questions for any reason, I do always respond to emails, and my contact information will be provided at the end of the meeting. All right. So I'll go through very quickly where we are here. I'm going to spend a bit of time on definitions of what I call empirical and explicit information or data, a little bit why it's important. We're going to get into talking about complexity of processes and things. And I will spend quite a bit of time on why there are gaps between what I call the empirical world and the explicit world. We'll talk about the realities of empirical data and how it can be used to close gaps. I'll provide a bunch of examples, I think, real world examples. Okay, we're clear to continue. Extrapolation of empirical data. I have several tools and techniques that I've used over the years that have been very, very helpful for me. I will close out with a discussion around contingencies and why they're important, and then we'll wrap up with some conclusions. So let's start with a bit of definitions about what I refer to here as empirical and explicit information. So we exist in two worlds, the real world and the digital world. And on the left, I've called that empirical or analog world, and the explicit and digital world on the right. And just so we all know what I'm talking about here, right? The empirical world is the real world. It's the world we see. It has real processes and real systems. It's the one we go to work in every day. We collect information and we can quantify actual characteristics of that world. And we can measure things like stope dimensions and grades and quantities and qualities and costs. And these are all physical characteristics that can be quantitatively collected and measured and evaluated. This world tells us how things are. They tell us how things will be. And I'd like to contrast that with what I call the implicit or the digital or explicit or digital world. And this is the modeled world. This is the world of designed processes and systems. It is a model of the real world. Now, we have characteristics here, of course, too, but these are calculated. Same characteristics, same geometries, durations, qualities, quantities, costs, etc. However, they are calculated. In this world, we live in a artificially created model of how things appear to be and how things might be. And I just want to make that characteristic or comparison very, very early in this discussion. So how things are and how they appear to be, and it's quite different. It's a representative model of the real world is what we're talking about. I would hazard to say that we spend the vast majority of our management and engineering time and effort living in the digital world. We're constantly updating forecasts and making predictions and budgets and assessments. And we spend, I think, hardly enough time and effort living in the empirical world, measuring and making use of the existing data that we have. So, always the question, so what, who cares and why is this important, right? My little business that I run, the engineering business, I spend a lot of my time explaining to my clients what is the difference between the explicit digital models and reality. I am often asked questions, fundamental and basic, that run like this. Is my next year's budget achievable? Why are we falling short on our production targets? Why can't we meet our cost and budget targets? Can I believe the feasibility study from company X? So I have a vested interest in continuing with the status quo, where the real world is very different from the digital world. But I'm convinced we can do a lot better. So over the past 20 years or so, we've seen an explosion in explicit tools and what's available to us to do our work. Very complex software tools, the likes of which continue to expand and grow on a daily basis. Our sponsor this evening, provides a solution that lives in the digital world to simulate what we expect to do with our minds. Unfortunately, the more complex these tools become, I still don't see a closure between the explicit view of the world and the empirical observations in the world. There's still a big gap there. At the same time, we're also exploding in terms of data collection and storage, right? The digital backbones, the whole data mining, the digitalization of our minds, et cetera. And, we're installing these systems exponentially underground. We're collecting huge amounts of data. And unfortunately, again, I just don't see that we're closing the gap between those two worlds, the real world and the digital world. I'm really encouraged by what I see in short interval control and planning. And again, a tremendous opportunity to collect real data about how we do work. But again, the gap exists. So I'll have a look at a mining project from an explicit point of view, right? And it's typical of what you might expect in a output from a major feasibility study, let's say. We have a scope or a design. We have a CapEx number that everybody's very focused on. And of course, we have some sort of schedule. After we build the project, then we focus on production, right? We make forecasts of tons and grades that feeds our revenue stream. And we deduct from that our costs. And I'll deal with those three costs today: CapEx, which I refer to as project CapEx; OpEx, which is your regular operating cost; and what I call SUSTEX, which is sustaining capital. And hopefully at the end of the day, we put out some forecast of profitability, typically expressed as NPV or IRR. So let's compare that now in a cross-check with the empirical data that we see in the real world where we've executed and constructed projects. And please feel free, correct me if I'm wrong, but these are my observations at least. So scope and design often oversimplified, CapEx overspent, projects run late. By the time we get to operations, we fall very short typically on tons and grade. Revenue suffers accordingly, and we also don't do a great job of estimating our OPEX and sustaining costs. And the sad outcome of all of that is that we are almost always disappointing our clients and our customers and our investors. So hopefully we can agree on that previous slide. And hopefully we can all come to face what I call here sort of the awful truth, right? And if we can't handle the truth, then maybe it's time to close the presentation now and move on. But I think we can do a lot better because fundamentally, I think mining companies still do a terrible job of forecasting. And I really think that the empirical data side of things holds some keys to addressing and overcoming that challenge. So I want to talk a little bit about our thought patterns that we use as engineers and managers. A very good friend and colleague of mine out of Hatch, William Kempson, he told me once that every process is complex once you start digging. And I think I tend to agree with that. And unfortunately, we live in a world with our human brains and limitations of our human brains and our thinking patterns, and our brains naturally shy away from complexity. We're unfortunately very good at recognizing patterns and classifying data, and we like to compartmentalize data and our experiences into some tiny little boxes, and the brain naturally simplifies things down as far as it can. And at the worst, we end up in this situation where we're thinking strictly in terms of binary outcomes. Things are on or off, good or bad, right? Yes or no. Binary thinking is extremely dangerous, not only from a social point of view, but also as a huge barrier to critical thinking. There are never or rarely simple outcomes, two simple outcomes to a problem. So virtually everything that we deal with is very much non-binary, right? Some sort of continuum of outcomes exists. And it actually takes a lot of effort to start thinking in those terms, to abandon binary thinking and move to this mode. Now, it gets even more complex when we have to come to grips with non-linear outcomes. And sometimes those complex problems are, subject to complex inputs and have very complex outputs. And at the extreme, of course, we start to deal with 3-dimensional, 4-dimensional, 5-dimensional problems. And the brain has a hard time dealing with all that. We'd much rather be back in the binary mode. So we really need to force ourselves as engineers and managers and to think in terms of complexity and try to overcome that inherent sort of laziness of the brains we have. So I guess my point of going down this road is really to suggest to you that overly simplified models of a very complex world will usually lead you to create a model that has some fundamental flaws in it. And I would also suggest that the use of explicit tools, by their nature, drag us down into binary thinking and oversimplifying models. And this leads me to get into a discussion about the explicit or digital task trap. For those of you that have done some work around levels of work, you'll be familiar with this little chart here. It's from Elliot Jacques, and it represents sort of the cognitive capacity of people as they grow and mature over their career, and what level of work what complexity of work they're able to handle. And I've augmented those the two axes here a little bit. So along the bottom is typically shown as age, but it's really knowledge and experience, right? It's the sum of the age, knowledge, and experience of the person doing the work. And on the side, it's not just the time frame that they're capable of thinking within, but it's also the complexity of the problems they can handle. Along the bottom, we have a work regime or work zone that exists in a data-rich environment where we have clear metrics. This is task type work, and generally speaking, we have a fairly low impact on the outcome of the company. But as we move upwards and to the right in this chart, we move into a completely different realm of thinking, right? So we are data poor, we have conflicting metrics, we have to think strategically, and the decisions we make in that quadrant have extreme impact on the success or failure of the organizations we work for. Now, I want to be sure nobody misunderstands this chart, because just because people are perhaps working on tasks at what we call low-level work, it's not to imply that the people there have any less value than the people working in the top quadrant. It's about the work, it's not about the people. And again, going back to the way our brains work, the explicit tools we use often drive our thinking downward. They take us away from that, I guess, lofty goal of strategic planning and thinking, and they drag us down into this task type low-level work, because it's very hard to think strategically when we're worried about formatting cells in Excel and context for formulas, or connecting lines and sections in a CAD routine. So this is what I call the digital task trap, and we really need to fight hard to stay out of it and keep ourselves from being dragged down. The other part of what I call this explicit trap is confusing or mixing up the two terms of precision and accuracy. I'm sure many of you have seen these charts before, but I really wanted to use them to explain fundamentally the difference between explicit and empirical information. So if we're using explicit tools, we will often convince ourselves that we're generating a precise answer, and that precise answer will necessarily be accurate. And my observation is that's simply not true. We can, in fact, be extremely precise, and we can be precisely inaccurate, or maybe precisely wrong. Just because we're using explicit tools that calculate things down to the third decimal does not imply accuracy. On the other hand, empirical and analog information is generally accurate or correct. It certainly may not be precise. And the true, I guess, holy grail here is bringing together the explicit, which brings precision, and the empirical, which brings accuracy. So I really think this is what we need to do as engineers, is mate the two worlds, the empirical and the explicit. Now, I don't want anybody to think that I'm anti-tech, or that explicit or digital tools don't give us a significant advantage in doing our work, and they certainly do. But I think it's important to know that the tools themselves and the outputs from those tools really give us nothing unless we pair that with that knowledge and experience to interpret the outputs and make sure they're believable and they're interpreted correctly. Again, the simple fact that we have tools at our disposal, does not make us a Michelangelo. It's really marrying those two worlds where we can really truly shine and do what is right. So to underline, I guess, the power of what I believe the empirical data has, I'm going to reference against the typical mutual fund disclaimer. And any of you that invest will have seen this, will be very familiar with this, right? So, typically our mutual fund advisors will tell us, right, that anything that happened in the past is no guarantee of future returns or future performance, right? When you invest, you take on risk, and the value of those investments are going to change up and down over time, and you could lose money or gain money. And anything that happened in the past has no impact on the future. I'd like to, I guess, contrast that with what I call the mine operations claimer, not a disclaimer, a claimer. And this is what my observations show me, is that in the absence of a significant effort by management, the past mine performance is a complete and absolute guarantee of your future outcomes. And it is directly predictive of that performance. Yes, operating a mine has some risks, but it is reasonably predictable. And although your process steps will fluctuate over time and you'll have ups and downs, your KPIs, your main KPIs, will remain stable. Now, I can hear people disagreeing with me over the Ethernet here. But and I get it. If you don't believe that, though, then you might want to check yourself against this definition. Is that, by doing things over and over the same way we always have and expecting a different outcome is really the definition of an insanity. So we really need to challenge ourselves and say there's a different way of looking at things. So in this presentation, really what I'm hoping to get at is that we get a grip on reality and we bring some sort of change to the way we're thinking that will allow us to do things differently, so that we're okay expecting a different outcome because we're going to do things a little differently. We're going to talk about shortcomings and explicit tools. There's a whole raft of them. Usually we don't have enough data to accurately model the analogs. The geometries and characteristics are usually oversimplified. We often miss steps in the process. We don't take account of them. We often oversimplify the performance that we're going to get from each of those steps. We underestimate the resources required, and we overestimate the productivity of those resources. And we also fail to allow for the unknowns. And of course, anybody that's done contingency planning will remember there are two categories. One is known unknowns, and the other one is unknown unknowns. My point here is that in an explicit world, your process will not operate as smoothly as your tools will indicate. And every explicitly generated outcome will be missing something. And that relates to the tasks themselves, the time to do the work, the resources that you need to do the work, and the costs that are going to result from that. So, how do we overcome the shortcomings of those explicit tools? And I've got a few suggestions here that I have found have helped me in bridging that gap and trying to address some of the challenges. And the first one is stop living on Hope Island. I'll explain that in a little bit. Obviously, collect as much information as you can, but more importantly is to process and analyze that data. Collection alone is half or less of the solution. You really need to spend the time processing and analyzing. We need to be honest with ourselves on the application of that information. We need to do benchmarking and comparisons of the explicit results with the empirical data. I think we also need to build in peak and surge capacities because, as we know, we're going to miss something. and we have to have additional capacity. And where all else fails, we need to calibrate, apply contingencies and buffers. So I mentioned Hope Island, and I have a little anecdote on this. I often meet with clients and I conduct audits of their work, and a lot of that involves interviews, personal interviews with people. And when I'm interviewing them, I often listen very carefully to see if there's any evidence that they're living on Hope Island. And I once conducted a complete audit of mine planning processes at a small underground operation, starting with geology, working right through the annual, monthly, and right down to frontline planning and scheduling. And their process was impeccable. It was one of the best processes I've ever seen. Communication was exemplary. The tools and techniques were extremely robust. But they continued to come short on delivering. So why was that? The fact of the matter was that every single member of the team, from management to geology and engineers, even the maintenance and operating department, were living on this Hope Island. And what is this place, right? It's a little fantasy land that we go to as engineers and planners, where everything's perfect. It's filled with assumptions. It's right next door to the denial lagoon here. It's covered with these very steep hills of performance. It's a place where we can do better than anyone else has ever done. We can do things better, faster, cheaper, and safer. Everything is optimized, and there's no need for excess capacity, and it's a truly wonderful place. The problem is, as an old mentor of mine once told me, that hope is not a mining method. He's heard of cut and fill and blast hole and block caving, but hope is not in a mining textbook. So if you hear this word in your day-to-day workings with people at the mine site or in engineering offices, you need to jump on it right away. To me, this is the number one red flag that I hear, indicating that the plans are unachievable. And everybody knows it. The team is likely drowning. They don't even believe their own forecasts. And their use of the word hope is a cry for help. They are calling to you as the leaders to listen and to respond. And I urge everyone, beware of Hope Island. Don't go there. So let's have a look at a bit more of a concrete example here with regards to deposit definition and some of the challenges we have in overcoming some of the limitations of explicit tools. I got a lot of respect for geologists. I'm not one. They live in a tough world. It is extremely data poor, and yet they are expected somehow to make extremely accurate forecasts. They're expected to know the deposit size to the nearest ton, the shape down to the nearest meter, and shockingly, especially in gold deposits, they're expected to know grades down to, let's face it, hundredths of a gram. My math might be off, but I think that's 1 part in 100 million. It's pretty amazing when we're only letting them drill a 30 by 30 meter patterns, with a 2 1/8 inch hole. Which roughly equates to about 0.04% sample size. So what does the empirical evidence tell us? Well, we typically oversimplify geometries. And certainly it's not as complicated as this diagram shows. It's an extreme Mandelbrot equation here. But I'm sure it's not as simple as this either. And our modeling tools, unfortunately, often lead us to the example on the right, where they oversimplify, they create straight lines, planar surfaces. And I would hazard to say that oversimplification of geometry and the continuity of a deposit can lead to huge errors in mining method selection. We've seen repeated examples where the engineers did the best they could to apply a method to an ore body that didn't exist. Ultimately, this can destroy the value of the mine. In truth, we probably have something in between. It has some complexity to it. And we need to reconcile that to our models. Make sure that the models include enough complexity to reflect reality. Because we all know what happens to the geological model when the engineers get a hold of it. Because we're using explicit tools and because we're bound by certain geometries, we end up oversimplifying the mining method as well. So what can be done about that? If there's geologists online, they'll have a whole bag of tricks that can address this problem. Obviously, drilling is expensive, but the more the merrier typically. I've often seen people drilling tight patterns to understand typical areas. We have new tools and techniques in the numerical simulation world for conditional simulations. I find one of the best ways to go about modeling is to look for representative structural models. Look at regional variations in shape and continuity and apply that down to the local scale. Go out and find analogs. This is by far one of the best ways to learn about your deposit. Go and visit. I thank goodness the relationship between Vale and Xstrata, Glencore, now back in the day was so good. Otherwise, I think we would have made a terrible mess of the 153 deposit at Coleman Mine. I would suggest we don't do enough capping on gold grades, and I'm certainly open to discussion around that, but typically we overestimate grades, and I think we could do ourselves a better service by capping more aggressively. Reconciliation is another great tool which marries the modeling from the digital world to the realities of the empirical world, and we don't do anywhere near enough of that, even month by month, year by year, whatever time frame you choose. And lastly, we need to apply reasonable modifying factors and constraining shapes to the deposits. I made note of this last item because the current best practice from CIM was recently updated. And if you haven't seen it, it was, I think, published at the end of 2019. And they were adamant that we have to apply reasonable constraining mining shapes to underground deposits. I think it follows the same logic as we use on surface with open pits. And we wouldn't think of releasing a resource estimate on surface without running a whittled pit shell. And I would suggest the same thing needs to be done with underground deposits using some variant of a floating stope or mineable shape optimizer or some other routine. So we'll have a look quickly here at mine plans and what the empirical data says. I had the great pleasure of attending a conference presentation by a guy named Pat Smith, AMC Consultants in PDAC 2019. And he did some very interesting benchmarking. He went out and he found 4 mines that were roughly the same. They were ramp access, fairly shallow deposits, all developed in a similar fashion. And he was looking for trends. And the first thing he noticed was that we never make our grade. And it's a significant problem. It's 10, 15, 20% shortfalls on grade. And I know I mentioned we shouldn't be thinking in binary fashion, but I'm going to break that rule right now. And I'm going to go out on a limb and say I have never in my career seen a mine deliver on grade, ever. And I'm hoping some of you can counter that with a few good examples. But we typically get grade extremely wrong. So, what do we do about that? Well, what we do is we try to overproduce. And this is the other trend that Pat indicated or found was that our ramp ups are typically slower than we expect. However, once we get to 100%, that's not good enough because we've messed up the grade. So virtually every mine has to then overproduce and overproduce significantly, not just a few percent, but in some cases 20, 30% more. And why is that? Because we still have to make up the metal count. Of course, the problem is this all comes at a huge operating cost because you're producing 30% more, 20, 30% more for essentially the same metal. So the lessons here, I guess, we need to plan on getting a lower grade from the deposits. Whatever our explicit tools are telling us, it's wrong, and we need to plan for increased dilution or factor our grades accordingly. I believe me, you won't be wrong. Again, I would suggest that I have never seen dilution less than what was in the plan. And the upshot of this is we basically have to build in capacity to overproduce in all of our mining projects. We have to allow for a way to recover metal value through increased production. I want to talk a little bit about process mapping as a tool to bring together the digital and the analog world. And I mentioned earlier that we often plan, overplan and underdeliver, and there's quite a few causes of this. One of them is failing to understand our processes. And I always encourage people to develop a process map before you attempt to quantify anything with regards to production or performance of that process. And I'll use a very simple example that everybody's pretty familiar with, right? Long hole stoping, drill, blast and muck, and fill. 3 pretty simple steps. Often that's all I see in schedules. And when I start tracking actual performance against those activities, I see that we fall short. We do not perform at the rate, and we don't perform in the timeframes that we expect. Now, the truth is, of course, we know a lot more about these processes. There's a huge amount of additional steps that we need to understand, recognize, and work into our estimates. Of course, between each step, there's going to be some form of delay. We don't operate our mines like an F1 pit stop, right? We do not have endless resources just waiting for the previous activity to finish before we jump in with the next activity. So we need to factor for these delays, and then we can roll them back up to a more simplified sequence. Now, I want to acknowledge here this delay that I'm talking about. This is not unknowns. This isn't ground failures. This isn't power outages. These are real delays that will occur because the driller finished drilling halfway through his shift, and he has to move out. Chances are the heading is going to sit idle while the blasting crews get ready to move in. So this is not contingency. This is real time, real measurable delay time in those activities. So what does one of these process mapping exercises look like? Well, this is a very simple tool I like to use, and I know we may have some simulation specialists on the call today, but a relatively straightforward process. If you haven't done it, it is enlightening. What I usually do is put a spreadsheet like this together with all the activities, and then I gather the experts, right? The operators, the shift foremen, the engineering planners, and we just work through the list one by one. And basically ask the following question: what is the worst you could possibly do? What is the maximum time this task might take? What do you expect it to take? And what's the best you can do? What's the minimum time? And I would suggest that by the time you finish running this exercise, you'd be shocked at the degree of variation, the amount of variation in your cycle times, where you thought there was zero in terms of delays. and 0 in terms of handoff between activities. I once did this exercise at a mining company on a fairly routine mining method. It wasn't long hole, it was actually a cut and fill operation. And once we completed the exercise and we showed the tally at the bottom, the feedback we got from the mine superintendent was as follows, and I quote, "We can't possibly be that bad." Yeah, unfortunately, the actual performance data we had from a similar operation nearby said completely the opposite, and that we were in fact that bad. Again, good and bad are sort of extremes. The fact is that the exercise we conducted reflected the reality of the actual data and the actual performance being achieved. We do have to be a bit careful about using this data, because one thing it doesn't allow for is the unexpected delays. So this is the things like I mentioned earlier, the power outages, the ground failures. And I suggest that these data really need to have a little bit of contingency applied to them, because they are missing those process interruptions. And I would suggest a 10 to 15% factor on those be used to put them in line. I'll get a little bit more specific here, deal with some actual data. This is an underground operating mine, and it's real performance data of various activities. And so I'm a big proponent of using empirical data, but it doesn't come without disadvantages. The good news is that empirical data includes highs and lows, your down days or 0 days, and it does represent the variation you have in your process. And it's generally a good indicator of long-term average rates. However, you do have to apply some caution, because sometimes you're fed information from the engineering department or the client that is only representative of best case or only representative of worst case, and so you do have to treat this type of data with a little bit of caution, and make sure you have an ample number of data sets before you start aggregating and making assumptions about averages. We're going to have a look, drill down here, literally on a drill down. And this is the drilling history chart from the previous slide. And so we can rapidly do a bunch of calculations, and I'm sure you've done these types of things. You can get some averages very quickly from the data source. But we have to be very careful in understanding our data set. So here is an example where we really do have 2 different operational modes represented in the same data set. And unless you dig in a little bit, you're not going to recognize that. So in this case, we had 1 driller working on at least 3 days. And of course, the performance isn't what you would expect. So we need to separate out those different operating modes. And at that stage, we can start making some statistical assessments, right? So anybody doing statistical process control will be familiar with the averages and upper and lower control limits. And again, make sure that if you have a different mode of operation, you separate that data and run a separate analysis on it. The good news with this data, or I guess the good thing from this data, is it can be very readily put into a dynamic simulation tool, which can really give you a much better indication of what your performance will ultimately be. We're going to have a look at the mucking chart, because there's a couple of very interesting things here that I think we need to be aware of when we're looking at empirical data. First of all, it's highly variable. There's 5 or 6, maybe 7 really, really good days, and there's a bunch of 0 days. So first of all, I guess we have to recognize this might be the way the mine operates. There are days when we don't muck the stopes, whether it's prioritization of other stopes or equipment being down, or whatever reason. We're not overly interested in the reason. We're really interested in the performance of this activity. And we have to recognize some data is lumpy. It's very highly variable. So again, we can go ahead and calculate sort of stats and use that in our modeling tools. And again, we're using empirical data to calibrate explicit modeling tools. Now, the one thing I want to highlight here is that achieving the average, the middle line, is contingent on actually achieving some of those peaks. And it's really important that we actually achieve those peaks. Otherwise, when we clip this data out, we're going to affect the averages. And I see this often where the engineers will try to smooth out a schedule. Whether it's mucking or drilling or blasting or whatever it is, they try to smooth it out and set caps on maximum performance. I would suggest this is very dangerous. So the assumption is, of course, that if we clip the data, that production will magically appear later on in the schedule, and it will fill in a gap. I would suggest this is unlikely. In fact, it rarely happens. We don't know what those conditions were for the peak performance, and we have no guarantee that we're going to be able to replicate that later on those days where we have poor performance. And when you clip or smooth out the schedule, all you end up doing is negatively impacting your averages. So next time you're looking at your 12-month schedule and you see that your mine produces exactly 6,000 tons every day for 12 months in a row, you might want to question the validity of that schedule. It's a red alert for me when I see overly smooth schedules. So rolling this data up, taking all the different activities into account, can serve as a great benchmark. And here you see a benchmarking exercise that I did for a proposed mining project in Northern Prairie province that shall remain nameless. And what we were able to do was to generate a whole stope sequence in Deswick, and then plot the performance of each of the stopes on this chart. So as you would expect here, the chart's not a surprise. As the stopes get bigger, your productivity goes up. They're just more efficient. The thing we found, though, is when we applied the benchmark with very similar mining methods, very similar depth, same regime, similar deposit, we found in general that the Deswick outputs, the average Deswick outputs, which are in orange, generally trended about 10-15% higher than the benchmark. So what we actually did at that point was then recalibrate our Deswick tools to soften, if you will, the expectations on production. Now, you could always argue that the benchmark was a poor benchmark, and certainly we're attempting to do better. I do get that, but those improvements need to be hard, concrete improvements that prove you will actually do something radically different than the analog just down the street. Another area that I really find is lacking in empirical analysis is metallurgy. We all know that metallurgy is becoming much more complex. Easy ore is gone, mineralogy is complex, deposits are less homogeneous. We often have different zones within the deposits, and the criticality of making an accurate metallurgical model is extremely high because it feeds directly into revenue. And you'd think that there would be some level of effort that goes into this. And unfortunately, again, in my experience, reading a lot of the scoping and even pre-feas studies, the attention to metallurgy is appallingly low. I often find their assumptions around metallurgy to be very simplified. And given the challenges coming in this field, I would expect us to do better. But again, we often fail to really recognize the complexities of metallurgy. And in fact, In this particular example, all the press releases, all the cutoff grade calculations, and all of the 43101 studies were based on a 96% recovery all the time, day after day, regardless of head grade, which we know is has a direct impact on recovery, and regardless of any metallurgical differences. What they were doing was basically just asking the mill, what's your mean recovery over the last 6 months? And they said 96%, and they ran with that number. Well, let's see how well that plays out. You can see the scatter here in the data, right? So what we did was we said we can do better, and we certainly need to do better. So we were able to very quickly, of course, contain the data with an upper and lower curve, which can be modeled mathematically. And from that point, we were then stuck with what's going on between those two lines. And we went into a little bit of a deep dive on this with our metallurgy team at the mill. And we had some expert help from XPS out of Sudbury on some basic lab testing. And we were actually able to find the basic cause of that. So what we were seeing was a fundamentally different performance based on the nature of the deposit. So often in these deposits, you'll get zones which have what we call free gold, very low sulfides, and recovery is always good for free gold, regardless of grade. And what we found was that any drop in performance was directly linked to the presence of sulfides in the feed. So once we discovered that, we were able to very quickly calculate a representative and accurate recovery of any block within the mine based on simply the head grade of gold and the sulfide content. So this was then fed back into setting their cutoff grade strategies. And I think the learning from all of this is that metallurgy is one of the more complex processes that we have. We often treat it lightly, and it doesn't have to be that way. We collect a lot of data, we can do a lot of testing, and we really need to do a lot more homework on metallurgy. The final section, I guess, here of my talk, I'm going to deal with operating costs and how I believe empirical tools can, fundamentally change the way we look at costs. And operating costs can basically be broken down into two components: one, a fixed and a variable component. And anybody working in the cost field, this is old news, of course, but for the benefit of this presentation, fixed costs are those costs that don't change with production, and they're basically fixed on a time basis. So it doesn't matter if you produce 1,000 tons a day or 6,000 tons a day, you still have to run the dewatering pumps. The other component is variable, and these are those costs directly related to production. So, if you're producing more tons, you expect to use more explosives, and those can be expressed as dollars per ton of materials. I do, in my observations, and again, looking at empirical data across many mines, is fixed costs are extremely high in underground mines, extremely high, at least 60%, if not much higher. Whether we hoist today or not, the costs continue to flow. So what this does is makes operating cost extremely sensitive to production rate. So we're going to deal a little bit with theory here. It's very simple. We can express the unit costs for any production rate in terms of fixed costs and variable costs. And when we put those two together, we get a very nice characteristic cost curve, which generally has this sort of exponential drop-off shape. And I created this one just in an Excel spreadsheet. I set the fixed cost at 40 million per year, and I set the variable cost at 35 bucks per ton, and that's the curve we get. So how do I extrapolate that as a theoretical calculation to reality? And it was deliberate on my part that I was able to determine the fixed and variable components of the costs for this particular mine so that I almost exactly matched the actual curve. So here we've now calibrated a cost model right down to an equation with real empirical data. I no longer need to worry about not counting the tape measures and the miscellaneous supplies. I now have a characteristic cost curve for this mine over a very wide range of productive outputs, production rates, that can fairly accurately predict the costs of my operation should I choose to increase or decrease production. I've been using these techniques for many years, and I've come across, it's one of the first things I usually do when I'm investigating costs at a mine. And so here's a mine cost, set of mine cost curves, all generated from real data, this one in Europe. And what we were able to do in this example was we were able to break out the individual cost curves for two mining methods in use at the mine. And by establishing those two curves, we can pick any production rate, in this case, 1,700 tons per day, and I can predict the operating costs of each of those mining methods. And so long as I know the relative proportion of each of those methods, I can then pretty accurately predict the estimated operating cost for the mine as a whole, for the entire mine plan. And so this tool became extremely important when the mine was revisiting its cutoff grade targets and trying to find an optimum production plan that mated production from both of the different mining methods. We were experimenting with splits 75-25, 25-75, 50-50 blends, and we had a very rapid tool to quickly feed back exactly what the costs would be into some very high-level strategic calculations that rapidly pointed us in the right direction for the optimum blend at this particular mine. Another mine, this one in south of the border, south of the American border, so a South American operation. And in this case, for any given production rate, we're actually able to break out specific departmental costs. And in this case, I show G&A, the mining cost, the direct mining, the total OPEX, and the top line is the all-in sustaining cost. In this case, at 3,100 tons per day. So again, very rapid tool, simple to use, and reasonably accurate in terms of cost forecasting. This case, another one is we had three different mining methods. We had a narrow vein cut and fill, we had an open stoping method, and a post pillar cut and fill. And we were able to generate independent cost curves for each of those methods, as well as a rolled up total for the entire site. We extrapolated the data to the mill as well, and we were interested to find out, how useful would a tool like this be if we're radically changing the way we operate the mine. And in this particular case, the mine switched its processing methodology from flotation only to a combination of both CIL and flotation for a period, and then was contemplating moving to CIL only. And so by taking their empirical data, we were able to regraph it into those typical cost curves that you saw on the previous charts. So we were able now to generate a fairly robust cost forecasting curve for fairly wide range of production for both the existing operations of flotation and CIL plus flotation. And then we were able to estimate where we expected the CIL only curve to be. These curves formed the basis of a trade-off study on the overall mine strategy going forward. The same tool applied to open pits works exactly the same way. extremely revealing information, and very interesting in terms of its coefficient of correlation. So really good matching of the data to the curves. Again, fully backed by the theory or the explicit calculations, but now fully calibrated to the empirical. In this case, any scenario of production from the open pit on a month-by-month basis or year-by-year basis could very rapidly be evaluated, excuse me, for operating costs against any of the three proposed mill processing options. What surprised me was that recent work I've done is that the same logic and thinking can be applied to capital costs. This is what I refer to as like project capital, upfront capital. And in this particular case, we had only one initial design point, and this was an explicitly generated bottom-up capital cost estimate. What we were able to do is, using the same concepts of fixed and variable splits, we were then able to extrapolate what the likely capital cost would be over a very wide range of production performance. And when we graphed that as a cost per unit per ton, we found a very interesting inflection point where we expected we could see a significant change in the profitability of the mine. So there appeared to be a natural break point of production below which the capital costs would have a massive impact, and above which the capital would become less impactful. We're currently working through detailed trade-offs on this particular analysis. So I want to, I guess, wrap up here with just a couple more curves and then a concluding slide. Empirical tools and empirical data, it need not be feared. It is generally quite accurate. It is perhaps less precise, but is extremely useful as a calibration tool and as a forecasting tool. I show this graph because we've all used the Taylor curves. At some point in our career, early stage evaluations, quick look at ore bodies, we've gone to the Taylor suite of curves, which have been expanded by many people, including recently by Smith and McIsaac, which gives us a rough and dirty way of assessing the potential of a deposit. So the Taylor curves are very familiar to us, and they can be extrapolated, and similar tools can be developed. So here's a rough and dirty tool that I use for very early stage assessments. It presents a series of 3 or 4 fairly well calibrated cost curves against production rates. Unfortunately, I haven't got a lot of benchmarking for sub-level cave and block cave methods, which are well off to the right-hand side of this curve. But knowing at least a little bit about the potential mining method and using the Taylor curves to take a rough stab at production rate, we can very quickly make some general assessments of what the costs are going to be. Now, these are op costs. And with a simple application of a design chart like this, I can very quickly assess what I think the sustaining capital costs are going to be. And a very similar tool can be developed for mill costs. Again, knowing approximately the production rate and the type or nature of flow sheet you're going to be using, again, you can make some pretty reasonable, fast estimates of what that operation is going to cost you. And again, sustaining capital can be tacked on top. So where does all this leave us, I guess? We have lots of data we collect, lots of empirical data. Processing it, analyzing it, and applying it is a good way of calibrating our explicit models. I go back to the earlier slide where I said that you can't possibly model every single step in a process, and that every explicit calculation you make will require some form of adjustment or calibration or contingency. And so I'd like to, I guess, summarize here and say activity complexity needs to have contingency. No matter what you come up with in your explicit scope design, there will be things you miss, and those need to be factored for. The resources that you estimate, the bottom-up estimates we do for labor, materials, and energy will all miss something, and they need to be calibrated. The time, the duration, the schedule of our activities is one area that I almost never see contingency applied to, and yet one of the biggest challenges we face is completion of projects on time. So again, I would recommend explicit analysis of your schedule line by line, factoring in contingencies for the things we've missed and those unknowns that we expect to occur. Normally, we see contingencies applied to capital costs. I almost never see it applied to OPEX and again to sustaining capital. My position on this has changed in the last 4 or 5 years, and I absolutely would expect to see a contingency placed on any bottom-up OPEX or any bottom-up sustaining capital. Unless you are extremely well calibrated against an analog, or you are checking and benchmarking your costs against, the previous year's costs, then those costs need some form of contingency applied. No matter how you slice it, something will always be missed in explicit estimates, and we can use contingencies to close that gap. So conclusions here today, we have to ask ourselves, do we really want to know the truth? I believe we do. I believe the days of the fly-by-night mining camps are gone, and we really need to know the truth, and our investors are demanding it. We have to recognize problems. Problems are complex, and we often oversimplify them. Explicit tools and techniques do have limitations. I recommend the use of process mapping again as a calibration tool. Collecting data is important, but more importantly is processing and applying that data so that we can calibrate the results from our explicit planning tools. Benchmark, internally, externally, regionally, and globally. Find analogs and test yourself against them. Ask yourself, what is it about my project that will put me and my team in the upper 10% of global performance? And if you can't answer that you have the best resource, the most experienced team in the world, then clearly you need to make some form of calibration exercise. I believe discrete event simulation is a great tool to close the gap. I'm a big proponent of simulation. So if our friends at SRK are listening, there's a bit of a plug for you. And I know Pierre Lebrec very well. Again, I'm not endorsing one company over another, but consider discrete event simulation in your forecasting. I believe AI has a huge potential to start integrating empirical data on a real-time feedback basis into explicit projections. And I firmly believe in broad-based empirical data to give you very quick and dirty evaluations on your projects. So to close up here, that's again, thank you for sparing your time and sharing your time with me tonight. Please remember, mining involves people. Everything we do is all about people. We build tremendous things, but it all comes through the commitment and passion of the people doing the work. And whatever you do, especially during these times of COVID, maybe where we can't socialize as much as we can, spend time with your immediate family, get out there, have fun. Life is short, make the most of it. And I'd like to thank the organizers again for providing me the opportunity to talk tonight.
Right. Thanks so much, Brian. It was funny when I saw those pictures. Not only did I recognize your family, but I think I recognized that orange Lamborghini Gallardo. I think I might have driven that same one. I recommend it as a great way to blow off some steam.
Yeah, I can't recommend. That was by far the best birthday present I've ever received in my life, and I thank my lovely wife for giving me that. And not to be exclusive here, she was my co-pilot for the entire day, and I was a little bit shocked in this day and age that the organizers would ask her, can you drive stick? And to which she replied, get in the car and I'll show you. So anyway, we had a great time.
Nice. Yeah, well, it's funny because Sean Kautzman and I got it for a Father's Day one year, and I think it was based on maybe a conversation you might have had with my wife. So thank you for that. And I'll thank Sean for asking the first question. So while I'm asking the question, if anyone has a question, you can raise your hand, ask it, unmute yourself and ask it if you like when you're recognized, or you can type it in the chat room. So Sean's question is, hi, Brian, if you start a project with incorrect data and assumption, it is very possible to see the impact of these inaccuracies compounded as you move through the project and mining life cycles. Every mine is unique, but based on your experience, are there certain processes or components that affect the economics more than others? And he gives some examples: exploration, engineering, mining operations, milling, etc.
Yeah, so if the people that are listening today, they're involved with projects, would be very familiar with that chart that shows the maturity of the project and our ability to influence the outcome. And so I think Sean's absolutely right that early stage errors, if they're entrained into your project and they're not captured early, they are going to cause you massive problems down the road. Problems from which you may not be able to recover. So in the hierarchy, the big hierarchy of things, when you're estimating and putting your mine plans together, you need to ask just that question. If I'm calculating the diameter of a pipe, how likely am I to be wrong? And what is the likely impact of me being wrong? So in that type of methodology, you can very quickly risk assess which ones of those key inputs are likely to be the most impactful. And therefore, what additional energy should you put in to make sure you're right? And I think the simple answer for Sean is, getting the deposit wrong, right? Whether it's size, shape, continuity, that's a huge issue, is continuity, right? And again, our tools like to connect dots, right? They like to make simple surfaces. Continuity of structure and grade is a absolute fatal flaw. Anything you do after that, what type of drill you pick and what development rates you pick and everything else is all moot if we fundamentally mismatch the deposit to the mining method. So to me, that's the one where I see project collapse, a complete, total project collapse. You can recover from getting your drift sizes wrong. You can adjust your level intervals, partway through. There's lots of those operational things we can tweak. But if we've mismatched the mining method to the deposit, all bets are off. Yeah, you got me passionate on that one. Thanks for that great question.
The next one's from Mark Crane. So it says, Brian, why would you use average statistical limits for such long periods? Would it not be better to minimize your time period to shift basis and allow your statistical limits to fluctuate with reality?
Yeah, great question. Yeah, so I used a term in here that I hadn't used before, and I hope somebody caught it. It's something called rugosity, and it's something a mentor of mine threw at me not too long ago, by a guy by the name of John Gill, and he was on about rugosity, and I think it goes exactly to what Mark has asked. So rugosity is the level at which we see variability on a small scale. And I absolutely agree with Mark that we almost have to go down in some cases to the next granular level, right? So I often look at data on a monthly basis, so it's aggregated. That's only fine for very high level. You need to drill to the next level, which typically is days, and then typically after that you're down to the shift by shift basis. And it depends, I think, Mark, on what are you looking for? You're looking for a directional estimate or a strategic alignment of what is the right strategy, or are you looking to optimize process? If you're looking to optimize process, Mark, you hit it on the head. You're down to detailed time studies. You're into inter-shift breakdown of all the steps, and now you're into that Six Sigma world where you're looking to move the bar a few percent. So huge increase in effort and relatively, let's say, moderate return. But when you're optimizing process, that's exactly where you are. You're in that world of the minutia, the shift by shift, the in shift time breakdowns, the delay analysis, all of that. But I would put it to you that going to that level of rugosity, of looking at variability on that fine a scale, would unlikely move your ship significantly. So that's kind of where I would break that, is that you need to look at the data at a level that's applicable to the problem you're trying to solve.
It's I can actually comment on that, Brian. What I'm talking about is you're trying to do forecasts on quarterly basis and yearly basis, but sometimes the rugosity on a shift basis or even a daily basis, because when I was the chief engineer, I actually monitored productivity by crew and by day. So, and you could see the difference between a Sunday day shift and a Thursday night shift, and that reflected things, right? And so that's what I'm looking at. If you're trying to get better at forecasting for shorter term.
Sure. So absolutely. When we've all worked at operations where there's a different shift schedule on the weekends, right? There's a different the maintenance crews work at different shift schedules, and that's where you have to go into the data. As you said, you got to go in and look at what's driving. Why do I always have poor performance on a Sunday afternoon shift? Is it the crews themselves? Is it something inherent in the way we do the shift changes? Yeah. So yeah, don't get me wrong there. You have to break out the data and say, well, why am I having that variation? What are the fundamental drivers there? And maybe you'll reveal something that can get you a bit of a step change too. Yeah. Some of it's cultural, by the way. We've all worked in mines where there's just a way of doing things, and it's a cultural momentum, and it's very hard to overcome. I would say cultural momentum is more difficult to overcome than a technical problem.
Great. Thanks, guys. Thanks for the question, Mark. So the next question is actually from me, and it's around contingency. And I do agree with you that, allotting time contingency is important. And actually, Mark has a question about that after. But my question is, after the geologists are done with the resource estimate, you have your block model, as say a short-term or a medium-term planning engineer, how do you apply contingency to the metal?
To where, Neil? I'm sorry.
Metal, either the grade or to try and.
Yeah. So there's two areas I find that we struggle with grade assessment, right? And it's a continuous process, right from the initial block model, right, where we're using numerical methods, geostats and whatnot to try to estimate the grade. So it starts there that you could have a fundamental analysis error, right? I mean, it could be capping or anything else. There's other technical ways of addressing it. But at each step along the way, there are opportunities, or is potential to introduce a calibration. So typically, you'll get your block model and you'll say, look, the grade of the stope is 5 grams. But then, we're going to apply our dilution. So that's the mining side, right? That's your opportunity to modify grade. Then typically we get our grade control people that are now, supposedly on a shift by shift basis monitoring the grade of the deposit, and you get that daily report from grade control. Again, my experience is that even the grade control people are likely to be overestimating. So there's another opportunity to calibrate the grade. And the last one is that calibration between the mill head grade and the final tails or sales of metal. So there's actually an inter-mill efficiency opportunity to calibrate. And when I review those processes, I look at each of those and I ask the question, what calibration factor do you use to take your block model before you hand it to the mining engineer? And often I get a blank stare. Well, we don't. Okay. Then I ask the mine engineer, what do you apply? Well, I apply dilution. Okay. Is it enough? Have you benchmarked? Have you checked? Well, we're light. Okay. Well, why are you not fully allowing for the dilution that is going to happen? Well, we expect we'll do better. Okay. So what are you doing that will guarantee a different outcome, right? Otherwise you're in that insanity loop of, well, we just hope that it's going to get better. Okay, well, the track record is X. Why would you predict anything else if you're not going to do anything different? And then don't be afraid to hold the mill to account, right? And look at their calibrations and their losses, because that's another opportunity. The other place I find grade going off the rails in a mine plan is failure to include for incremental ore. And incremental ore is that material that has some grade, but is thought to have already had some of its costs paid for. So that's that broken muck on the ground in a development heading. Do I throw it in a stope as backfill, or do I hoist it? And you'd be surprised when you look at your actual numbers to what you planned, how much of that incremental was actually built into the plan, and how much more did you actually ship? And I often find there's a huge gap in what we planned as incremental and what we actually shipped as incremental. And that can lead you down a path of chronically being short on grade.
Great. Thanks, Brian.
Incremental ore is a slippery slope to unprofitability. I'll leave that little anecdote, little statement with everyone.
Great. So seeing as we're coming to the end of the time, the last question again will be from Mark, and then we'll finish up our night with a quick presentation from Hexagon and Northern Survey Supply. So Mark asks, if you add contingency to duration and schedule and then add contingency to cost, are you not compounding your contingency, i.e. time is money?
Yes, good point. So I would suggest that adding the time is adding that fixed cost, right? So your labor productivity goes down. So I would suggest that the cost of schedule increase is more in your indirects. So you're not going to use more rock bolts just because you're going slow, right? So I think you'd have to split it on that kind of fixed and variable and say, look, if it's going to take me a bit longer, I'm not going to consume more material. I'm not going to pour more concrete. I'm just wasting labor. So that the costs you need to look at are they direct or indirect? And if they're indirect, I think they need to go in as an additional cost, not just a contingency. I find contingencies in the true sense of the classic sense of the word are more about we got the quantity wrong or we missed an activity. It's not about I drag my schedule out. I don't believe that classic contingency cost is linked to schedule extension. And I think schedule contingency not only allows you a higher probability of achieving the schedule, but it also forces you to acknowledge that time is in fact money, and you need to factor for it separately from the direct contingency on, oh, I wasted more concrete, or I put in more rock bolts, or that those sort of quantitative type things. It's an excellent question though, And I grapple a little bit with how to factor for the cost of schedule extensions. I'm more interested in, did you schedule every activity back to back to back? And if we have a power outage, you're guaranteed you're going to lose 3 days that are unrecoverable. That's what I'm more worried about with schedule extensions. But excellent question, because it does link that time and money in terms of contingency. I'd be interested to see what maybe the PMI has to say about that kind of guidance there. Yeah, thank you.
All right, thanks, Brian. Thanks, Mark. Yijing, can we move on to the slide? So this is Hexagon Mining, and I'll invite Matthew Brown, who is the Business Development Manager for Northern Survey Supply, to please share a few words.
Thanks, Neil. No, I really appreciate being here, be able to sponsor this event. I had the pleasure to talk to Brian a few weeks ago about this exact subject. So it's always nice to hear him go into more detail. I know he can talk for days on end if you let him. So yeah, just some background. So some of you know us as Northern Survey Supply. We've recently rebranded as NSS Canada as we move to being more of a full mining solutions provider outside the geomatic space. We've also recently partnered with Hexagon Mining, which is what I was talking to Brian about a few weeks ago. Hexagon Mining is a mining technology solutions provider that covers a lot of the data aggregation that Brian was talking about today. And one of the major objectives we have is to bring some of that information technology software to the mines in Sudbury and the underground space to help people actually manage the data. We're getting to a point where, especially when I was a geologist, we're collecting so much data that we don't use. And so much of it just gets thrown in spreadsheets and Excel documents that we don't really follow what it's doing. So I just want to get the word out there that there is technology coming to help really bring this back to real life applications and really factor through some of the noise. So I just want to say thanks again for allowing us to sponsor this, Brian, and it's always a pleasure to hear you talk.
Yeah, and again, I want to make sure that I don't leave anyone with a taste that I'm a technophobe here. I cannot run any of the current software tools. I'll admit that. Dinosaur claws on the keyboard. But the degree to which they have opened up our ability to rapidly explore alternatives. And I've gone out of my way in the last couple of years just to try to keep my finger on the pulse of how rapidly things are growing and changing. And you guys, Hexagon, have a phenomenal package there. And encourage anybody who's looking to acquire or otherwise get into the a more advanced mine planning and scheduling tools to certainly give yourself and your team a call and spend some time looking at your products. Yeah.
Great, thank you both. So with that, thanks again, Hexagon and NSS Canada. Thanks, Brian. Thanks to everybody who attended tonight. We had really good turnout. I saw up to 43 people. Appreciate the 27 people who stayed on till the end. And we look forward to seeing you at the next GMM. So everybody enjoy their night, and we all look forward to getting back to the time when we can have a beer or a glass of wine at Dynamic Earth. But in the meantime, please come to the CIM meetings and please stay in touch. Thank you. Have a great night.